So basically, conservation of energy states that energy at the beginning is going to be equal to the energy at the end. For this lab, we're going to be focusing mostly on kinetic and potential energy. There is also thermal energy and other energy, but that is approximately negligible. So how we're going to demonstrate this is we're going to have an inclined plane, and we are going to roll various objects down the plane and record their velocity at the end. So for this, the energy is going to be potential energy plus kinetic energy. Now at the top, potential energy is going to equal mgh. And kinetic energy, since the object is not moving, will be 0. So that'll be plus 0. Since we've chosen this height to be our height 0, our potential energy at the bottom is going to be 0. And for our kinetic energy, it's going to be rolling kinetic energy
rotational
plus the translational kinetic energy. So for our rolling kinetic energy, it's going to be 1/2 the moment of inertia of the object times the angular velocity squared. And for our translational kinetic energy, we are going to have 1/2 the mass times velocity squared. So the energy, since this is the energy at the bottom, it should be equal to the energy at the top because of conservation of energy. So since this is given, we are going to solve for velocity. So we're going to have mgh equals 1/2 moment of inertia velocity squared plus 1/2 mv squared. We're going to solve for velocity and compare that to our recorded results of velocity.
We need five objects with different moments of inertia. A hollow sphere, a solid sphere, a hollow cylinder, and a solid cylinder. Also, a donut. Specifically, we used, for the hollow sphere, a racquetball. It's pretty dense. But not as dense as metal marble? What's the marble made out of?
steel.
A steel marble. And a hollow cylinder, a bronze hollow cylinder. This, for our solid cylinder, it's brass, and a donut, which is just the inside of a tape. The other equipment that you will need, if you want to be like us, is lots of Pasco stuff. A ramp, 2 clamps, one for the top, one for the bottom, a speed sensor, an 850 universal interface, and non-Pasco laptop, ruler. Once you have all your accoutrements, set up the ramp with a bottom clamp to stop the rolling object once it gets to the bottom, and another at the top to keep the height at the specific height that you want. Additionally, you want to make sure you have your motion sensor at the top connected to your computer and your Pasco interface. Here is a view of our actual procedure. It's a donut.
No, it's not. It tastes like plastic. So, minor clarification on this object. We were referring to it as a donut in the lab, but a more accurate name is a hoop, or a thick cylinder hoop. And this is also the only object where the moment of inertia is actually dependent upon the radius. So, as you can see, I've written a relationship up here, and it is that the velocity is inversely proportional, or directly proportional to all of this, inversely proportional to the square root of 1 plus a. And I'm going to show why this is true. To do that, I have to express the moment of inertia in terms of the mass and the speed. And the way I'm going to do that is to write the moment of inertia. When we're talking about our moment of inertia for 4 out of 5, it can be summed up in this equation. A certain constant times the mass of whatever we're working with times the radius squared. And by radius, it means the radius of the object from the center to the edge. And now I'm going to use it to substitute into the moment of inertia over here. So, In order to get rid of this omega, this is the rotational speed. The rotational speed has a relationship to the linear speed, v over r, where r is the same radius we were talking about originally, and then v is the linear speed, which is the same v over here. So you can see when we substitute all of this in, it becomes a simpler equation. Now, in order to simplify this equation, I'm going to plug in everything that it just proved. We still have mgh on the left side. We have 1/2 mv squared that hasn't changed either, but I'm going to rewrite this term of the equation. We have 1/2 moment of inertia, which is amr squared, and the rotational speed, which is v over r, but it's also squared. So v over r squared. Now, this simplifies because, as you can see, mass is in every single term, so we can cancel it out. What we're going to do is there's also a 1/2 in front of every term on the left side, so I'm going to multiply both sides of the equation by 2, so that it cancels out everywhere except over here. So I have 2gh on the left side. I have v squared, because the m is out and the 1/2 is out, plus a r squared times v squared over r squared. And now, as you can see, the r squareds can also cancel out. And we're left with 2gh equals v squared plus a v squared. And to simplify it even further, we have 2gh equals v squared times 1 plus a. And then to solve for v, I'll write it up here. We have the velocity equals the square root of 2gh all over 1 plus a. And since these are constants, this relationship that I showed you at the beginning is true, because when a varies, v also varies. We did not vary the height in our lab, and the acceleration of gravity did not vary either, because we're at a constant elevation. So then, therefore, this would be the relationship. Here we have the 5 a's for each constant of moment of inertia, and we have 1 for a hollow cylinder, 2/5 for a solid sphere, 1/2 for a solid cylinder, 2/3 for a hollow sphere, and this ugly mess for what we like to call a ring, but a more accurate name would be a hoop.
For our solid sphere, and as you can see, we have the calculated velocity, and then we have the mean of our 10 data points that we took in lab for the solid sphere, and we calculated standard deviation and error. These are our results for our hollow sphere. Again, we have the calculated velocity, the mean, median, standard deviation, and the error. Here are the results for our solid cylinder. Here are results for the hollow cylinder, and here are results for the donut moment of inertia, or the thick cylinder. As you can see, most calculated velocities lined up with our means, and a couple of them were different. For example, our solid cylinder moment of inertia graph, you can see the calculated velocity was quite different from the mean. This is due to experimental errors, since when we were rolling the solid cylinder down, it would make a lot of noise, which shows that a lot of energy was being released in the form of sound. We observed something similar with the hollow cylinder, where the calculated velocity is quite different from the mean. There's energy lost in the form of sound, because these two in particular, the hollow cylinder and the solid cylinder, made a lot of noise when they were rolling down the plank. As you can see, we graphed a plus 1 versus the velocity squared, and there is a negative correlation, which is what we expected. The r squared value is 0.9, and again, the reason why there is a not super great r squared value is because of the experimental error due to sound and heat being lost while we were rolling down the objects.
A flywheel is a mechanical device which uses the conservation of angular momentum to store rotational energy, a form of kinetic energy proportional to the product of its moment of inertia and the square of its rotational speed.